Welcome back. This is the fifth and final video in the hypothesis testing series. Um, so this is sort of to tie everything together, and you're going to get the most out of this video if you actually do pause the video when suggested, try to work the problems, and then resume watching the video to check your work. Okay, so here's a reminder of the 7 steps I'd like you to follow. And here's your first problem. So it's commonly held belief that 98.6 degrees is the proper human body temperature. But in a sample of 50 healthy adults, the mean body temperature measured was 98.26 degrees Fahrenheit, with a standard deviation of 0.77 degrees. Is there enough evidence at the 1% significance level that the true mean human body temperature is different from 98.6? Okay, so try to apply the 7-step approach. Give it your best shot, even if you're not sure, and then you can pick up with the video and check your work. All right, I've copied the problem up top for reference. Now, when you first see a problem, the first thing you got to do is figure out what test you're actually going to do. Okay, so you'll want to notice first, what is the variable here? Well, we're looking at body temperatures. So that's numeric. So we have one sample of individuals in which a numeric variable was measured. So what can we do with that we've learned so far? Well, we could test the population mean with a t-test. Okay, so in our hypotheses, we'll be using the symbol mu to represent a population mean, specifically the true population mean body temperature among all healthy human adults. Under the null hypothesis, the commonly held belief, unless proven otherwise, is that the mean is equal to 98.6 degrees. However, if there's strong enough evidence, we could rule that out and say that there's a difference. And in this case, we're just looking for any difference, not necessarily less than or greater than. So we use the does not equal sign. Right, we're indicated to use the 1% significance level, so I'm going to represent that as alpha equals 0.01. All right, we need to check the necessary conditions and make sure you're checking the conditions for the t-test rather than the z. Okay, so with the t-test, when we think about normality, we're checking for normality of the sample mean x bar. And recall from video 4 that there's sort of 2 things that could happen. You either have a large sample of 30 or more measurements, or you have a small sample of less than 30. In this case, 50 people had their temperatures measured, so that's a pretty large sample. Large enough that we can say, well, the central limit theorem has got us covered. It's safe to assume a normal distribution for the sample mean. We don't actually need to see each measurement and make a histogram or a box plot in this case. All right. Well, our sample size of 50 we said is pretty large. We wouldn't want to be too large, though. If it's above 10% of the population size, then we'd have a problem with independence. Okay, so remember the quick little trick is to add an extra 0. So if the population has at least 500 members in it, then we're okay. And of course, if we're looking at healthy adults, there's billions of them in the world, so we're not even close there. Lastly, our data needs to be unbiased, so from a random sample of the population. All we know about this sample is that they're healthy adults only. So as long as we keep our inference restricted to healthy adults, we're probably okay if we assume that it's a random sample from that group. Okay, since it's a t-test, we're going to use the formula, which is the t-statistic. So we'll put in the sample mean first, the hypothesized mean, and that's over the standard error of the mean, which is S over root n, the sample standard deviation over the square root of the sample size. All right, so that works out to be negative 3.12. With the t-distribution, we also need to think about the degrees of freedom. So that's n minus 1 for this one sample t-test, leaving 49 degrees of freedom. All right, so if we imagine that bell-shaped t-distribution, our test statistic puts us in the left tail because it's negative. And our alternative hypothesis was simply that there was a difference. So we don't have an arrow saying, go left or go right. Rather, for this two-tailed test, we're going to look at the nearest tail, find that area, and double it. Okay, so the area in the left tail would be everything to the left or towards negative infinity from negative 3.12 with 49 degrees of freedom. So in the left tail, it's 0.0015. We're going to double that to also account for the right tail, leaving our p-value at 0.003. Then we employ our decision rule, and our p-value, 0.003, is indeed less than the significance level, 0.01. So this is another situation where we should reject the null hypothesis. That is, we can rule out that the mean really is 98.6. All right, and to interpret this, bring it all back to temperature at the 1% significance level. So we're saying we have very strong evidence that the mean body temperature among all healthy adult humans is not equal to 98.6 degrees Fahrenheit. So this commonly held belief probably needs updating. All right, one more problem. I saw a study that claimed that 15% of people with iPhones are currently using a cracked iPhone. So let's suppose you're interested in testing if that percentage is any different among iPhone users at Rowan University. So you have a random sample of 120 Rowan students who use iPhones, and 21 of them had a cracked screen. Is that enough evidence at the 5% significance level that Rowan students differ from this population at large, which we're going to assume that this 15% is kind of the true known value? Okay, so pause the video and give that a try. Okay, so what's the variable here? Should we test a mean or should we test a proportion? If we go down to the individual level, what are we looking at? Well, we're looking at who's using an iPhone with a cracked screen versus one without a cracked screen. So that's categorical, and hence we'll test the proportion. Now, if we're taking this study as kind of the truth that 15% of iPhone users have a cracked screen, we could represent that as a proportion of 0.15. And we're interested to see if that percentage is any different at Rowan. So is the proportion any different in either direction from 0.15? Okay, and our parameter that we're testing is now P, a proportion, and this is a proportion of all Rowan students who have iPhones that are cracked. We were told to use the 5% significance level, which is where the alpha equals 0.05 comes from. Okay, so we need to check the conditions associated with the test for proportion. So we do start off looking at normality again, but we check it a different way from in the previous problem. We check it using n times p naught and n times 1 minus p naught. So 120 is our sample size, and 0.15 came from this 15%. We saw that number in our hypotheses. Okay, so these results, 18 and 102, we want to make sure that they're both at least 10. If either of them is less than 10, we wouldn't be able to do this test. But fortunately, they are. Okay, for independence, again, check that we have not exceeded 10% of the population size. So if we have 120 in our sample, 10 times that would be 1,200. So as long as there's at least 1,200 Rowan students with iPhones, then we're okay. I'd say that's a pretty safe bet. Lastly, we were told that these Rowan students were selected at random, so we can be assured that they're going to be representative of the whole population. Okay, so we now need to compute our Z statistic. A preliminary step here is we need to find p hat. So that's just the proportion in the sample that had this characteristic of the cracked screen. So that's 0.175, and that'll go up here. So we see that in the sample, the proportion with cracked screens was a little higher than the study saying 15%. Is it significantly higher? Well, for that, we need to incorporate the standard error to figure out. Okay, so substituting in the hypothesized proportion of 0.15 and our sample size, punch that all into your calculator, you should obtain about 0.767. So that's our Z statistic. Now, the Z statistic, there's only one of them. We don't need to worry about degrees of freedom here. So we're thinking about the Z distribution. And our test statistic here is positive. There's no negative sign. So we're on the right-hand side of the Z distribution. We wanted to see, is there evidence that the proportion of Rowan students was any different? So that could be either greater or less than. So like in the previous problem, we're going to find the area in the nearest tail and then double it. It's just that this time the nearest tail is on the right. Okay, so for this standard normal distribution, we can find the area under the curve, starting at our test statistic and going to a large positive number, like positive infinity, on the standard normal. So there's about 0.22 in each tail. We double that, we obtain our p-value of about 0.443. All right, so our p-value, how does it compare to the significance level? We finally have a problem where this p-value is larger than alpha. 0.443, clearly a lot larger than 0.05. So the decision is we should fail to reject the null hypothesis. And like I warned you about in videos 1 and 2, that doesn't mean that the null hypothesis is true, just that there was not strong enough evidence to be convinced that it isn't. So a good way to word this interpretation is, well, at the 5% significance level, we did not find strong enough evidence to conclude that the proportion Rowan was any different than the proportion in the whole population. Okay, that leaves open the possibility that maybe there really isn't a difference. Maybe the slight difference we saw between our study and 15% was just sampling variability. Or maybe it was a defect of our study, like maybe we just need more data. Or maybe an error occurred. So any of those really are possible. So that's an example of how you might word your results carefully if the null hypothesis cannot be rejected. All right, so hopefully these videos have helped you got caught up or perhaps just reminded of what you learned in Stat 1. If you need more practice, there are a lot of other videos out there. And I do also recommend reading the appropriate chapters in your Stat 1 textbook as well. Okay, good luck in the upcoming semester. And if you're in my class, I'll see you soon.